Thank you, Mr. Chairman. Ladies and gentlemen, as you heard already, we do the presentation together, Mr. Toell and I start. What we want to talk about is about design challenges for urban transport systems. Design, we're speaking about the track design. Our presentation has the following content. After a brief introduction, I will talk a little bit about structural design of ballastless track forms. Mr. Toell then will present vibration mitigation possibilities, especially with mass spring systems, and how we determine the insertion loss of such systems. And then we come to some practical experience. We show two examples. One is the track system for the Doha Metro system in Qatar, which will be under operation in the next year. And the second is an example of the track system of the Vienna underground system. Why ballastless track system and why urban transportation track systems? In the last 20, 30 years, we find like a renaissance of the public transportation in cities. In the 1950s and 1960s, there was the strategy to allow the cities to be the transport with individual vehicles, with motor cars. And then the number of cars increased very quickly and showed that this concept has no future. Therefore, now many cities install public transportation systems. Maybe I want to mention that in Doha, until now, no public transportation exists. So the whole traffic is done by individual cars. And the Doha Metro system is the first public transportation for this city. So even in such countries where they have very cheap fuel, it looks like they changed to public transportation due to the high amount of traffic. They cannot do anymore with individual cars. What are the requirements for such track systems? Of course, we need high availability because the trains run up to every 3 minutes. For example, in Vienna, the narrowest gap between two trains is below 3 minutes. This means very high availability of the track is needed and high performance. This leads to very strict requirements for the track. And therefore, ballastless track systems are here necessary sometimes, especially to avoid constraints of the availability. And we have also the situation that we have very tight curves in metro lines, and therefore high lateral forces. Their ballastless track systems are sometimes better than ballasted track systems. Also, we have a very small space, especially in the tunnel lines. And all this together leads, as mentioned, to the ballastless track systems. What are the main challenges for such systems? The available required space is one of the crucial things. The height and the width which is available is very small and very, very tight. Also, the manipulation space for the construction phase is sometimes very, very small, very restricted, especially in the tunnels. When we think about this tube from the London Underground, it's a very small tunnel, and to manipulate there the components of the track is very critical. And of course, the maintenance concept is very important. So we try to develop systems which are more or less maintenance-free. Of course, we know that maintenance-free is not possible, but low maintenance is the issue. So then the loads which we have to take into account are, of course, the vertical loads, and as I mentioned before, the high lateral loads especially. Temperature and all these things have also to be taken into account. The next thing is the question of settlements and the adjustability of the structure of the track structure for these settlements. It's not very seldom that we have station and tunnels, and in between station and tunnels there occur different settlements due to the different construction principles of these civil structures. And therefore, it's needed to find a solution where these different settlements can be adjusted in the superstructure. Vehicle dynamic is another parameter which has to be taken into account, especially the allowed displacements of the track, the deflection of the track under train load. And also the question, for example, of transition zones was mentioned in the morning session, the question about transition zones. We also use this 1 second rule and try to make a transition between different stiffnesses within a length of the track which a train passes in 1 second. And then we have also to take into account different subgrade constructions. We have for metro lines in the inner part of cities, we have tunnels, and then we have the embankment sections, and afterwards we have then the sections, the elevated sections on bridges in the outer parts of cities very much. So the ballastless track system should be able to fit for all these possible substructures. And the next issue is the dynamic design. And I give now to Hanno.
Yes, one of the issues of any track systems is the vibration behavior. What happens is usually quite clear. As the train is passing, an impact is generated at the rail wheel interface, and this impact is transferred to the track system, and it excites the outer boundaries of the tunnel, which then again excites the surrounding ground. So the vibrations are transferred over the ground to the buildings that are located on the side and on the top of the tunnels. And in the area of the foundations, the building is coupled and amplified, and the vibrations travel to each of the floors. Inside the floors, we have persons living, we have people sleeping, and usually there are well-defined limit values inside these buildings that need to be respected. So what can we do if we cannot fulfill these limit values? We can implement mitigation systems. Mitigation systems can be implemented on each of these parameters, but the most cost-effective one is to implement them in the track bed, basically by installing mass spring systems or any other mitigation measures. How is this working? Usually, the train represents a mass and springs, and also the track bed is represented by a combination out of masses and springs. In this case, for example, we have the mass of the car, which is damped by, well, with some very low frequency, usually above 1, 2, 3 hertz. Then we have the undamped wheel set mass. We have, it's basically the bogie and the axle. Then we have elastic elements underneath the rail in the fastening system and in beds underneath the rail. We have again a mass plate, which is this green bore track slab in this case, that is loaded on an elastic component. And again, we have a mass underneath and again an elastic system. So all of this is a combination of different masses and different springs with different stiffnesses. And what we need to do is to determine the so-called insertion loss, which is basically the behavior of the mitigation system. This can be done by multi-degree of freedom models or by finite element computations. More in detail, the multi-degree of freedom model represents all these masses and all these springs, and as you see here, it can be represented by a matrix out of masses, one out of stiffnesses, and one out of the damping. And once we know all the parameters of the material that is used within the system, we know all these values, and we can solve this equation for the displacement. We do this displacement determination for a standard track, which is the undamped track, so as a reference track, and we again do this for the mass spring system. So we have basically two deformations. Once we have the ratio between these two parameters, we can define the insertion loss. Basically, the insertion loss has a very remarkable point, which is the natural frequency that is a characteristic value of the mitigation behavior of the system. I will come back later and hand the presentation over to Dieter.
Yeah. Now we want to show you some practical experiences we gathered in the last years. The Doha Metro system is, I think, very well known. It's a complete new metro system with a line length of a track length of about 170 kilometers, more than 100 units of switches and crossings, depot facilities, and so on. And it's completely new, a new system in a city which has never had before any public transportation. The concept consists in the phase one of several lines. We have here the red line, the green line, the golden line, and the blue line. And the reason why they now installed this system is because of the soccer championship, which is held in 2022 in Doha, and therefore they said we need a city which has a public transportation. What are the specifications for this system? We have their cars with 16 tons axle load. We have a minimum radius of 168 meters for the track. And we have vibration mitigation necessities according to a noise and vibration study, which we have also to perform ourselves. They had a noise and vibration impact report at the beginning, or environmental impact report, and defined several critical areas. And the whole study for noise and vibration was based on the FDA standard from the United States of America. And next point is we have very limited height of the system available for especially on the elevated sections. I'll show you later on. And also a limited self-weight of the system allowed on the elevated sections due to the load carrying capacity of these viaducts. In the tunnels, we have the problem with the space for manipulation. And we have a very restricted and stringent time concept for the installation of the system. We started with the design in 2015, and in December this year, the lines are finished and will start with operation, so it was very restricted time for the whole design and construction process. This leads to the necessity to use a precast system. This system was developed together with the company POR and is based on the Austrian slab track system Oberbau, which is a prefabricated slab, consists of prefabricated slabs. The Austrian system, the slabs are 2.4 meters wide and 5.1 meters long. We adapted this system, reduced the dimensions of the slabs. The slabs are now only 4.1 meters long and the width is 2.1 meter to make it possible to manipulate the slabs in the tunnels. We have distance of the rail fasteners of 700 millimeters for the straight sections, 650 millimeters for radius down to 250 meters, and for lower radius we have 600 millimeters distance of the rail fasteners. We use a modified rail fastening system, modified 300 system, specially modified for the needs of the urban transport system there. And we have a derailment containment. This was mandatory for the whole line, and we integrated this derailment containment into our prefabricated slab. Furthermore, we had the need that a lot of crossings, of cable crossings, have to be installed between the system. Therefore, we increased the gap between two adjacent slabs from 40 millimeters, which is the standard for the ÖBB system, to 100 millimeter to allow these cables going through. You see here some of these slabs already fixed in a position just for checking whether the positioning of the slabs is possible. The rail is a 60E1 rail, a very heavy rail for this axle load, but this is a general tendency which we can see in international projects that they use very heavy rails for metro lines due to the wear. You see here some typical cross sections. This is a cross section on the bridge. We have only the height of 470 millimeters from top of rail to the top of bridge deck. And we have also tolerances in this bridge deck, so it's very limited space available here, which means that we have a grouting concrete thickness of 80 millimeters maximum. And then we connected the bridge deck with our system by such stirrups, which were post-drilled into the bridge deck. You see here also the situation with the third rail. I come later on to this. Cross sections for the tunnel. There are two different types. The standard type, where we have no noise and vibration mitigation measure necessary, where we have just to install on a finished first stage concrete our system, also with a total construction height of 47 centimeters. Also 80 millimeter in situ concrete here is installed. You see the slab width is 2.10 meters, very, very small system. In areas where we have to mitigate noise and vibrations, we have to install this whole system on a continuous floating slab, which is shown here. How do we solve special problems? For example, the transition between a straight and a curved section. We developed several transition slabs to follow this transition curve. So these are different slabs with, to construct the cant in the ramp, and also to come to, for example, from a straight line to a radius of 350 meter, excuse me. Second important thing was the fixation of the third rail system. There were two possibilities. One is to post drill. This is one possibility, and the possibility we used finally was to insert some dowels already in the molds and give therefore the possibility to fix the third rail. So, back to you.
So, based on the noise and vibration report, we needed to implement different systems in order to maintain the required limit values. We have this heavy mass spring system that you already saw before. It's a floating track slab on single discrete point bearings. And we have this so-called light mass spring system, which has a higher natural frequency, lower mass, and a full surface bearing, which is marked in red. So basically, we varied the natural frequencies also for the heavy mass spring system, depending on the requirements. We came down to 6 Hertz, 8 Hertz, or 11 Hertz as required. The lightweight mass spring system also shows 11.4 Hertz, but it shows a different insertion loss in comparison to the heavy mass spring system. As you might already understand, the installation of this system, it's much more complicated than the installation of this system, because this is basically a bottom-up construction, and this needs some specific adaptations in order to be built. Because the question is, how are we able to place the bearings underneath the concrete block? Now, the first idea was to use prefabricated precast elements as lost formwork, but due to the space conditions, we were not able to do so. The tunnel has a diameter of only 6 meters, and we needed a different approach to build this, given the very strict construction time that we were able to use. So we decided to include a separation layer here between the first stage concrete and the future mass block, to cast in situ this concrete block and to provide some cavities for jacks. Once the concrete is cured, we placed these jacks, we lifted the entire block, and we managed to place the bearings. Also, one of the requirements by Qatar Rail was to have a replaceability concept for these bearings. So the system works, as I already said. We will place the jacks, we again will lift the block, and we can replace the bearings very easily. Here you can see one of these maintenance openings. Of course, it's quite narrow. The people working here need to be very, I might say small in order to get in and to change these bearings, but it's possible. It was tested and it perfectly works. So another problem in the case of the heavy mass spring system are the lateral forces, because obviously the system can carry the forces in vertical direction. This is not an issue, but especially in curved sections, we have also the lateral forces, and we needed to implement a system where we could allow the forces to go to the lateral part. We designed this lateral retainings. Basically, this is an element out of PTFE. It has a coating in Teflon, which allows the system to move in vertical direction, but it blocks the system in lateral direction. And this was also tested by means of vibration impact, because of course the vibration mitigation behavior should not change once we install these bearings. And due to the Teflon coating, it was perfectly possible to fulfill the vibration requirements. In case of the light mass spring system, of course, the lateral forces, they can be handled much easier because we have this trapezoidal shape, so the system is blocked anyhow. One of the next challenges was how to implement a system for switches and crossings. In total, we have 118 switches and crossings within the network, and we invented or we adapted the bore system, and we provided 169 different types of slabs, which you might be able to see here, based on the position of the rail. The slabs were designed in a manner that we could install the switches and crossings in a very precise way. So now I will jump to Vienna once again. This is the metro network in Vienna. It was developed within the last 50 years. There were some historical lines like U4 and U6 that got transformed to metro lines 50 years ago. And the first line to be installed was the U1. And it was the first real metro line where a ballastless track system was implemented. Now there is a new project ongoing. It's basically the extension of U2 line towards south and the small piece of U5, which is currently in phase of tendering. And I will just explain you how we developed the track systems for these new sections. Basically, in 1969 on U1, the first track system was installed. It was called Alter Wiener Oberbau, so the old Vienna system. It was a ballastless track system with plastic sleepers in rubber boots. So it has a monoblock sleeper loaded on plastic boots on a concrete plate, and the concrete plate was again loaded on an element that was sealed mineral wool panel. It was sealed because, of course, the impact of water should be prevented. However, it turned out after 25 years that this sealed mineral wool panel was not perfectly working and fulfilling the long-term behavior that were expected. So in 2003, after 25 years, it came to a revision of the Vienna system, which resulted in the Neuer Wiener Oberbau. It's the new Vienna system, which basically includes now B-block sleepers that are loaded in rubber boots, again the concrete base plate, and now instead of the mineral wool, we are using polyurethane. It's a product of Getzner, it's the Silomer, and as you can see, the natural frequency was decreased from 23 to 18 Hertz, so we have better mitigation behavior, and this system was also installed since 2003 within the network. But something happened again. In 2006, a new train type was introduced. It's the train type that I was showing also this morning that shows worse emission behavior in comparison to the former trains. It has a slightly increased axle load, but something else was also happening, the introduction of the 24 hours metro service during weekends in 2010. The Austrian limits for noise and vibration, they are depending on the service hours of the trains. So when we have overnight service, the limits, the allowable limits, they were decreased. So now we have an additional problem. As you might understand, these two parameters, they are not matching in favor. So we needed to implement a new system. There was a requirement for a further improvement of the track system, but there was also the requirement of maintaining the main characteristics because deformation, signaling, and electric characteristics, they were quite successful of the previous system. So the newest system is now called Neuer Wiener Oberbau 2018 with the following modifications. The track slab has an increased mass, so the height of the system basically doubled. We have some shear dowels that now are designed for dynamic loading and not for static loading as it was for the last system. The fixation of the power rail is new, and also a new fastening in switches and crossings was implemented. As I already said, we have increased height. You can see that the mass block is much higher. We still have the B-block sleepers. The frequency now comes down to 12.8 Hertz. The axle load increased. And in switches and crossings, we have a special baseplate system that was implemented. Now, this is, for example, this joint, because due to constructability reasons, we built sections of 22.4 meters within the Vienna network. You see that all the structural reinforcement is located in this lower part. There is a second concrete pouring stage where we do not have any reinforcement, and we are now connecting these sections of 22.4 meters with this shear dowel, which is much bigger than the static dowel that we used before. It's this system, but it was the only system that was approved for dynamic load conditions. This is now the power rail as it was before and as it is planned to be installed now. Basically, the old system included an installation directly on the B blocks. Due to bad welding execution and due to the irregular deformations between the B block and the power rail, it came to, in some cases, it came to damages. And we noted that the deformations that were induced in the power rail from the power rail itself and the vibrations that were induced into the block from the wheel resulted in these damages, and so we needed to invent a new system. Basically, the new system now includes the installation of the power rail not on the B block, but directly on the slab track, which has the benefit that the vibrations induced from the wheel are lower because we have the damping element of underneath the B block, and the dowels are fixed in this base plate, and this is the new system. Switches and crossings, also here you see the previous system and the new system. Basically, we are not able to provide a system based on B blocks because due to changing geometries, this is a very hard task. So since ever, Wiener Metro Systems had mass spring systems, not based on B blocks, but on single fastenings with high elasticity. You see the elastic element, which was located underneath the base plate. And also here, we had difficulties because we have increased maintenance effort in such sections because we saw that the bolt started to loosen due to the vibrations. And this, of course, was not a very fancy solution. Now the new solution includes the elastic element underneath the rail, and we have the elastic bed basically here. We have fastening clamps instead of the bolt, and now we are having reduced vibrations that are induced to the bolts and a higher lifetime that is expected. This section was already installed some months ago, and we already had some investigations in regard to lifetime expectancy and to maintenance costs, and basically this system demonstrates that this maintenance issue can be reduced to a minimum. Now the conclusion, track systems are different, but what they all have in common is that they need to fulfill the requirements of the operator. They need to fulfill the requirements of the installer and the manufacturer. For example, in Doha, we had issues with temperature. We had issues because of this very strict installation time. In Vienna, we have other issues because we have highly densely populated city areas. But what really needs to be considered all the time is to consider all the different aspects and to find a best fit solution for each of the track systems.